So this is the heart dissection I was telling you guys I was hoping to get for you. So I'm here with my friend Dr. Curtis, and he is a heart surgeon. So he's very expertise in this area. So I thought it'd be fun to have him show you the heart dissection. I know we're not getting to do it together at school, but so you'll get to see an actual heart surgeon, dissect the heart, and he's going to be able to share with you some of the things that we're learning about in our book. So he's also my neighbor, so I'll let him start.
Hi. Well, we have a heart model here, and this is a heart model I use in my office a lot of times to sort of help inform patients as to what the normal anatomy of the heart is, and then we describe what may be their problem that we're going to try to fix. But this heart model is larger than the average human heart. It's probably a little closer to a cow heart, which we have here today for dissection, and probably closer to, at least in Alaska, what we recognize as maybe an average size moose heart. But it's the anatomy is very similar. There's only a few minor differences between those mammals and our hearts. And for instruction, however, they're quite similar. So this is a heart model. It is one of the organs that we have in our body, and it's obviously one of the more important organs that we have in our body. It is functionally a pump, and that's what its job is. It's oftentimes easier just to reduce every organ to what its main function is. So your skin is an organ, and it's there to actually insulate your body and protect it from the outside environment. The heart's function is to circulate blood, and therefore it functions as a pump. It's a complex pump, and it's made almost entirely of muscle. At least 90% of it is made of muscle. And so, but it's very unique muscle because unlike other muscles in our body, which have to work at times for maybe 5 minutes or 5 hours, this muscle pumps for an average person for 75 to 80 years on average, and it never fatigues. So it runs 24 hours a day, and it runs 7 days a week. And if it stops running for even a minute, it would be you would pass out and be unconscious. If it stopped for 2 minutes, you would probably suffer a very severe injury to multiple organs because they wouldn't get the blood supply that they need. And if it stopped for 3 minutes, you could possibly never recover. So it's important because it has to keep running, and it has to keep functioning and circulating blood in our body. So for instance, at nighttime, when your body is asleep and you're really not needing as much circulation, you're not needing as much blood pumping through your body, it is still probably pumping about 60 times a minute, and it's probably circulating about a gallon of blood per minute depending on your body size. So that's when you're asleep at night. When you're up walking around, it's probably beating 80 times per minute, and if you're walking fast or in any way exercising, it can easily get up to 100 times per minute, and if you get on a treadmill, you can easily get it to 140, 150 times per minute. Now, if you compare that to other muscles, just functionally, you can't take your hand and squeeze air, let alone squeeze the equivalent of a gallon or 2 gallons of blood through that action. But if you just squeeze your hand empty for 5 minutes, these muscles in your forearm would fatigue. And yet, this muscle is beating, as I say, probably on average well over 100,000 times every day. And so when you multiply that out times somebody who may be alive for 70 to 80 years, it makes you appreciate that this is very high performance muscle. It has to keep running all the time. You had this muscle in your legs and you went jogging, you could just keep jogging and jogging and jogging, and your leg muscles would never fatigue. So it can as a high performance muscle, it means all the cells, the myocardial cells, or myocytes is how you would describe that cell, therefore has a very high metabolism, meaning that it needs a lot of energy. It needs a good fuel supply of its own to actually create that kind of energy. And so that's what these big arteries are that are illustrated in red here. These are arteries that carry oxygenated blood and blood with other metabolites to the myocardium, or the muscle out here. And so you have to have these arteries have to stay clean and open and wide open, so that whenever you accelerate your body and you start running and jogging, that you can get all the blood supply that you need to your body. Now let's talk a little bit about that function. So overall, when there's 4 different chambers in the heart, and we're going to walk through that in a minute. But again, its goal is for this chamber here, the last action of this heart muscle is for this left ventricle, the biggest chamber in the heart, and we'll open this up in a few minutes, is to squeeze blood, and that blood ultimately comes out to this big blood vessel in red here, and this is called the aorta, A-O-R-T-A. And this is the thoracic aorta because it's the part of the aorta in the thorax, or the chest. And specifically we refer to this as the ascending thoracic aorta. And this comes out of the heart. It is carrying oxygenated blood, and blood that is chock full of all the metabolites that your body would need. And so this is very enriched blood that your body needs to function as well. And so it gets pumped out of the heart, and it comes up north here, and it comes up towards your neck. Now, every blood vessel that goes to every tissue in your body, from your scalp to your brain, to your eyes, to your chest, to your lungs, and all the way down to your toenails, is a branch that comes off of this aorta. So this aorta is the main pipeline that runs through your body. But in fact, the first 2 branches that it gives off go right back to the heart itself. So it comes out of the heart, and it gives off a branch, which is a little hard to see at first, but a branch that comes off of that aorta right here. You can see this little, there's a little mark here on the front. Yeah, it's usually right on the front here, a little black mark on the front. And that gives off the blood vessel that comes over to the right side of the heart. So it comes off here, and it comes off of the aorta, and then it travels in this sulcus, or groove, we call the atrium ventricular or atrioventricular groove. It's also called the sulcus because it's where the artery emanates from. So it comes down in this groove, and it just gives off all these branches that go out to the heart muscle. And then the same aorta right here gives off another branch that comes right off the back of the aorta, and it travels behind this pulmonary artery here, and it comes out right here. So it comes out here, and then it gives off this branch down the front of the heart, and then it gives off branches around the side of the heart. And we'll get into that a little more as we move on. But just to show you that every branch that goes to every cell in your body comes off of this aorta. So this aorta comes up north, and it travels up here, and then right around your chest, it has to make a U-turn because the rest of your body is below it. So it makes this U-turn, and that's what this area here is, right here. It's called the arch. So this is the arch of the aorta. And when it makes that U-turn, it also gives off all the branches that go to your head and your neck and your brain. And you can see these 3 branches right here, and they come off at the very top of that aorta, and they give off the 2 carotid arteries that you can feel in your neck, and they also give off the branches that go to both of your arms. After they give off those branches, this aorta not only turns to the left, but it turns posterior, and it travels along your spine. So it travels very close to the spine, inside of where the ribs are in the spine. So these would be your ribs, and this would be where your spine is. And it travels right there along that groove, because in that way it's able to give off all the branches that go to your spinal cord, which are extremely important. And then it also is these ribs provide protection, so that if you get hit in the back it actually protects this big blood vessel, because if in any way this gets injured, it is going to leak out all of your blood pretty rapidly. So that not only allows it to provide the blood supply to the spine, but it protects it, and it travels through your chest, and then it gets below the diaphragms, and the diaphragms are the muscles that provide bellows for your lungs. So when you breathe in, your diaphragms go out and help to bring air into your lungs. But right below the diaphragm, this aorta then gives off multiple major branches. That a big branch that goes over to your liver, another one that goes to the left and goes to your spleen, and then it comes down and it gives off branches that go to the small bowel region and the colon region of your stomach, and then also to both of your kidneys. And then once it hits your belly button, so if you look at where your belly button is, that's where the aorta then divides like pants. It divides into two major branches, and those branches go into the pelvic region, and then they travel down into your legs. So these arteries then get smaller and smaller, and they give off branches that get smaller and smaller, ultimately to the point that these arteries get to be so small that you really can't see them. So you've probably been cut, had a paper cut or something slight on your finger, and you just see blood welling up on your finger, but you don't actually see all the little arteries because they're microscopic. They're actually pretty small. A red blood cell is about 7 micrometers in size, and these little capillaries are not much bigger than that in diameter. And so they're actually, you need a microscope to see them. But ultimately, all the branches that come off of here perfuse all of the tissues in your body. And as that blood perfuses the tissues, like your skin, your liver, your brain, and all of those tissues extract out of the blood what they need. And what they tend to need are, they need oxygen, they need certain types of sugars, they need certain types of proteins, they need certain types of hormones, they need things like insulin. And so there's a lot of things that they actually need that is extracted out of the blood. So after it travels through those tissues, and those tissues extract those metabolites and the oxygen out of the blood, then the blood has to sort of make its way back up to the heart. And the way it does that is it travels through those tissues and then into veins. And veins are the way the blood returns to the heart. If we just quickly look at this heart model, you'll see that these arteries are in red, and they're illustrated in red because blood that is oxygenated actually is bright red. But once the oxygen has been extracted out of the blood, the hemoglobin changes a different color, and so the blood looks darker. And so it's always illustrated in blue, or a cyanotic color is what it's referred to. And so for every artery that's taking blood to the tissues, there is a vein that accompanies it that brings the used up blood, if you want to call that, back towards the heart. So it's like a two-way street. You know, you have one street where the cars go to their destination, and then maybe they drop something off, or like a cargo truck drops off its goods, and this is what blood is doing. It's dropping off all of these metabolites and oxygen. And then you have another lane that's going to bring all of those empty cartons back, and it's going to bring them back so that they can get replenished, and they can get reoxygenated, and they can get the metabolites regenerated and put back into the blood. And then you have to make a full cycle. So the way that occurs is, as I said, from below, those veins keep coming and they travel through your legs. And you say, well, I don't have a pump in my legs or in my foot, so how does that blood get back? You're correct. There is no pump in our foot. So the blood makes its way back by a combination of, when you lay down, for instance, the blood will then just flow back towards the heart. But also those veins, unlike the arteries, are very compliant. So they're very squishy. It's very easy to push in on them. They're very compliant. So when you get up and walk around, and your muscles then get very firm and tense. So if you go jogging, those muscles are squeezing down hard, and those veins are very compliant. So when the muscles push on them, it squeezes them down. And then what happens is you have one-way valves in the vein, and the valves only open in the direction that the blood can go up towards the heart again. So when you squish that vein, it pushes the blood. It can't go backwards, so it goes forward, and then it gets pushed back and recycled back up until it gets into the main veins in our body, and then it just sort of goes with the flow and makes the cycle. So it comes back in reverse. It comes back through those pelvic veins, and then right around your belly button, it comes back into this major vein we call the inferior vein, or inferior vena cava, to use the Latin term. And all of the veins from the diaphragm down, all of those veins coalesce into one big vein here, and the inferior vein, or inferior vena cava. Now it travels up and back into the heart, and everything from your head, your neck, and your brain, and your arms, all of these veins, they come together and coalesce into this vein, the superior vein, or superior vena cava. So these two veins bring all the blood back to the heart. However, on its way back to the heart here, this vein travels right through the liver. If my hand were the liver, it literally travels, this vein travels right through the liver. And so the liver is responsible for taking a lot of the food that we eat and that our stomach begins to break down with acids in it. And then our small bowels and large bowels break them down further. And that a lot of those metabolites go to the liver, which then creates the proteins and hormones and other metabolites that our body needs. And not only does the liver do that, the pancreas tends to make the hormones like insulin, and our adrenal glands, another organ, tends to make things like adrenaline. Adrenaline is what your body releases. If you go jogging and you see a bear in the woods, you need to get your adrenaline up so that your heart can race fast and you can run away from the bear if you need to. But that's what adrenaline does. And so if you get frightened, your adrenaline levels go up. So those types of hormones are created in the organs below the heart, and they actually get put back into the blood. So this blood gets sort of replenished with all of those metabolites from the liver, pancreas, adrenal glands, and even the kidneys put some hormones and such back into the bloodstream. So this blood right here is very rich in those metabolites. This blood up here is not. So now it comes back to the heart. So the heart then, as I said earlier, its primary function is as a pump, but it also is where all of this blood mixes. And so now we're back to the heart, and it's a pump. It's a 4-chambered pump. There are 2 chambers, right atrium and right ventricle. On the right side of the heart, there's a wall down the middle here called the septum, also made almost entirely of muscle. And then there's the left atrium and left ventricle. So this is not a 2-dimensional organ. It's obviously a 3-dimensional organ. And if you look at, when we look at these real hearts, you'll see that all of this stuff is sort of at an angle. So these chambers actually come through, and there's sort of a spiral structure to all of them, but it looks sort of flat and straightforward and simple here. But when you try to cut one of these in half, you see that it's not quite that straightforward. We'll get to that later. So let's get back to these 4 chambers: right atrium, right ventricle, left atrium, left ventricle. Now, the right atrium, this is muscle, and even though it's a different color, this is very thin-walled muscle, almost paper thin. At times you can almost see the blood flowing through this layer of muscle. But this is mostly a collecting chamber. So this blood comes in here and mixes with this blood here, so that now all the blood shares in the metabolites that has been restored to the blood. And all of the chambers are separated by one-way valves. So 4 chambers in the heart, 4 one-way valves. So this chamber collects the blood, and then it squeezes the blood through this one-way valve into this chamber, which is the right ventricle. You can appreciate that the muscle here is thicker than the muscle here. And that's because the ventricular chamber actually has the job of, the right ventricular has the job of squeezing the blood this valve closes, and then the blood goes through the second valve in the system, the pulmonary valve, but it actually has to squeeze with enough force to squeeze the blood up here and through both of your lungs. This chamber only has to squeeze it and get it from here into this chamber. And so that's why this chamber and the wall thickness can be quite a bit thinner. Now, it also works in synchrony, and so your heart beats with a very precise rhythm, so that each of these chambers fires in synchrony. So when this chamber has squeezed and is empty, this one is already full, so this one squeezes and fills this chamber. And so they beat in synchrony, so that this chamber doesn't just have to passively fill, it's actually actively filled, meaning this chamber squeezes and fills this chamber up, and it makes it so that those chambers are constantly being filled, and this pump can work very efficiently. As you can say, it's sort of like having a semi-automatic gun that's just constantly reloading the chamber, as opposed to one you'd have to open it up and put a new one in. So by having this chamber constantly fill this one is working very efficiently. So this chamber squeezes, this valve closes, the first valve, and this is called the tricuspid valve, and that's because it has 3 cusps. So tri, Latin for 3, tricuspid valve, or 3-cusp valve. This is also a 3-cusp valve, but they didn't want to repeat the same name, so they call this the pulmonary valve, and that's because this is the pulmonary artery. It is taking blood to the lungs. So again, this chamber squeezes, the blood goes through this valve, and then the blood comes up here. You can hard to sometimes appreciate it, but this vessel is splitting right here, just like 2 pair of pants. It's splitting. One side of it is going over here to the left lung, and the other one is going underneath the aorta, and it's coming out, as you can see down here. It comes out over here and it goes to the right lung. And so that's how you're now pumping blood into the lungs. So by pumping the blood into the lungs, you're trying to oxygenate it. So what happens is the blood is almost restored. It has all the metabolites, but it still needs the oxygen. So the blood gets pumped into the lungs. Your lungs are made of millions, or more likely billions, of little air sacs. They're called alveoli. And these alveoli, just picture like they're just like one single cell layer thick sacs that are in your lungs, and there's billions of them. And so they are sitting there, and my fingers would be the arteries that surround those cells. And so what happens is when you breathe in, air goes in and it swirls around inside of this little sac, and these blood vessels are on the outside. And so when that air swirls in, air is by nature 21% oxygen, so there's oxygen in that air, and the blood that's going over the top of it, it has hemoglobin in it, and hemoglobin has a high affinity for oxygen, so it actually extracts oxygen out of the air, and then it exchanges it for CO2, which is a byproduct of our metabolism. So then we breathe out CO2. And so we breathe that out, and now the blood, however, is reoxygenated. So now the blood out of the left lung returns to the heart through these 2 veins, the left-sided pulmonary veins. It comes out of the right lungs over here, back in through these veins here, the right pulmonary veins, into this chamber, which is the backside of the left atrium. So the left atrium now has blood that is oxygenated, it has all the metabolites, and it's ready to go. It just needs to be ejected into the aorta. And so this chamber collects that blood, and then it squeezes it. Again, when this chamber is collapsed, it squeezes it into this chamber, and this is the left ventricle. And it squeezes it through a 2-leaflet valve called the mitral valve, which is a bicuspid valve for 2 leaflets. But it squeezes it into this chamber here. This chamber has the thickest muscle because unlike this chamber, which just has to squeeze the blood through into the lungs, this chamber, when it squeezes, it has to squeeze with enough pressure and enough force that it can squeeze the blood all the way up here past this valve up here and into the aorta again, but it has to squeeze it with enough pressure that the pressure can go all the way up and perfuse your brain, your scalp, through all of your skin tissue and your liver. So that's why this chamber is so thick, and this is the last chamber in the heart. So again, when it squeezes, this valve closes, the blood goes right past it, and it travels right up through and past the last valve in the system, the aortic valve, and then it's made full cycle. So now it has made a full cycle all the way from, as I was pointing out earlier, how it comes up here. Well, now the blood's coming back up and it's coming up through here. So that's one full cycle of the blood, and your heart is, again, beating at least once a second when you're asleep, and more than that if you're sitting in a classroom. It's probably beating at least 80 times a minute. Again, the heart is very three-dimensional. A lot of this looks like it's just in one plane, but it's not. You can actually see that pulmonary valve and the aortic valve are right next to each other. They're sitting right next to each other. And the tricuspid valve and mitral valve, literally inside of the heart, are only millimeters apart. They are not that far apart. And so that makes a difference when we're doing actual heart surgery. So one other thing which becomes apparent sometimes in the heart models, or when we're dissecting them, is two things. There's this hole you can see right here in the right atrium, and this hole here is called the coronary sinus. And what that is that all of these veins here that are coming from the heart, they come back and they drain back to the heart, and then they ultimately drain right back into the heart right here in the first chamber, the right atrium, so that the heart collects its own used up blood basically so that it can be recycled through the heart. And then last but not least, and a little harder to see here, is you'll see this little indentation right here, and that's called the fossa ovalis. We should be able to see that in one of the heart models. All of us have a fossa ovalis, and when we're born, it's just an indentation. But when we're in utero, meaning we're still before we're born, that's an open hole, and that open hole allows the blood then to come. Oxygenated blood comes from your mother, and it comes and it feeds right back into this inferior vein, and then that open hole allows it to travel straight across into the left atrium over here and then get pumped out, because when you're in utero or before you're born, your lungs don't open. They're not opening up. Your mother is oxygenating the blood for you, and it's just being passed on to you through the umbilical cord. So that shuts down. It doesn't shut down in everybody, and there's probably 5 to 10% of people where it shuts incompletely. And so at surgery, oftentimes we'll see that it's open, and we'll add that on and just go ahead and close that off for people. If it stays open, there's a potential for people to have strokes, and so we tend to shut it and close it off. But I bring it up here only because we'll typically see it in one of these dissections. So that's a full cycle for a heart, and we're going to move on here in a minute to the dissection and make comparisons between a true heart and the heart model, so that we can try to make some correlation.